There was a question just like this on your test review. And I'm hoping you guys did the test review last weekend on Canvas when I posted the test review. But if you missed the test review, maybe you were really surprised by this question. I'll show you the right way to do it. And then I'll show you something that I saw in the papers that I really liked. That wasn't necessarily the right way to do it, but I appreciate it regardless. And what this says is an oil refinery starts production in 2009. So prior to 2009, they're not making any gasoline, diesel, whatever. But after 2009, they're going to produce gasoline at this rate, right? And so T represents years. T is time in years. And if I say T is 0, that refers to 2000, the year 2000. So between T is 0 and T is 9, there's no gasoline being made. But after T equals 9, we're making gasoline. We're going to make gasoline, indefinitely into the future. And also, we have a formula for local gasoline demand. So if you have a refinery in Joliet, Illinois, then the local gasoline demand means like the greater Chicago area. How much are the locals consuming of that gasoline that you're producing? And so if the refinery produces more gasoline than the locals are consuming, then you need to export the gasoline outside of your local market in order to find buyers for it, right? So exporting gasoline looks like, I don't know, like putting it in a pipeline and getting it to the Gulf and shipping it to Europe or whatever. But, just because transportation costs money, you're going to sell your finished products to the local market first before you start exporting outside of the state. In any case, the local gasoline demand follows this formula. And by the way, if your local demand exceeds your local production, then you would need to import products, right, to meet the demand. And so this question says, at what time does the local demand exceed the production rate for the first time? And so in the question, what we have baked in is this assumption that the production rate is going to start off higher than the local demand, and then at some point in the future, the local demand is going to start to exceed the production rate. So maybe production is decreasing and demand is increasing, and at some point in the future, you'll have to go from exporting your excess products to now importing products to meet the demand. And so that moment, when that happens, there's going to be one moment where demand is equal to the production rate. So we write this equation where I just set demand equal to production. And then we're going to multiply both sides of this equation by t plus 2. So I'm going to multiply the left side by t plus 2. And then when I multiply the right side by t plus 2, it's just going to cancel that denominator. So, boop. On the left side, let me expand this out a little bit. I'm going to get 1/2 t squared plus 2 times 1/2 t is plus t, and then plus 30t, and then plus 60. And on the right side, I have 30t plus 200. And then I'm going to subtract 30t plus 200 from both sides. So if I subtract 30t here and subtract 200 from the left side, I get 1/2 t squared plus t. 60 minus 200 is minus 140. And then on the right side, I'm going to cancel that out to 0. The last thing I'm going to do is I don't like the 1/2 in front of the t squared. And so I am just going to multiply my entire equation by 2 in order to cancel out that 1/2. And so 2 times 1/2 t squared is just t squared. 2 times t is plus 2t. 2 times minus 140 is minus 280. And then 2 times 0 is 0. So all I've done so far is I set my demand equation equal to my supply equation, and I've just used a little bit of algebra tricks to rearrange this. And now this is a quadratic, and so I can use my quadratic formula. And my quadratic formula tells me that negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. These are going to be the solutions to my quadratic equation. So for us, b is 2, so this would be negative 2 divided by 2 times 1, so that's negative 1, plus or minus the square root of b squared, so 2 squared is 4, minus 4 times 1 times 280. And it's a negative 280, so 4 times 280 is 1,120, and then I divide by 2. So the square root of 1,124 is not a nice, neat number. You would need your calculator for this. But luckily, you do have a TI-30 to use on all your exams. And if I do square root of 1,124, that's about 33.5. So 33.5 divided by 2 gives me 16.8. So it's going to be negative 1 plus or minus 16.8. And if we think about the case where I take negative 1 minus 16.8, that would be negative 17.8. And negative 17.8 corresponds to a time that's before the year 2000, and the oil refinery doesn't even start up until 2009. So I don't really care about that solution. What I care about is the solution negative 1 plus 16.8, which is like 15.8. And so the year t equals 15.8 is the year 2015 and 8/10, so maybe like September of the year 2015, right? And just to make sure, because we just did a lot of algebra and I'm very prone to making mistakes, what I should probably do is evaluate my supply function at 15.8 and evaluate my demand function at 15.8, and just make sure that these give me the same result. So let me do 30 times 15.8 plus 200 divided by 15.8 plus 2 is 17.8. And this gives me a value of 37.9. Okay, and then for the g equation, half of 15.8 plus 30 gives me 37.9. Okay, so it checks out. This is the moment in time where supply and demand are equal at 37.9 million barrels per year. Okay, so that would be your answer for the time t. That's the answer to the first half of the question. For the second half, between the year 2009 and the equilibrium moment, how much total gasoline must be exported? I'm going to do my best to draw a little picture of what this would look like. So starting in the year 2009, I have some curve that represents supply. Like how much gasoline are we producing at the refinery? And I'm also going to have a curve or a function that represents demand, or local demand. So the area in between these curves and by the way, my horizontal axis is time, my vertical axis is the rate, either the rate of consumption or the rate of production. The area between these curves is going to represent the total volume of gasoline that is produced but not consumed by the local market. Now the area between these curves is going to be the definite integral from 2009, which is t is equal to 9, and ends at this little equilibrium point, which was 15.8. And what are we integrating? Well, I need my top function minus my bottom function. And so my top function is that production f of t, and minus my bottom function, g of t, with respect to t. So I need to first figure out what in the world is f of t minus g of t. And here's a trick. And it's definitely tricky, so like, I don't blame anybody for missing this. In fact, I graded your exam in such a way, like basically I gave you an extra 10 points because I didn't expect anybody to get this last problem, right? So however many check marks, you got times 10 plus 10, that was your exam score. But anyways, I didn't really expect anybody to get this, but maybe from your last algebra class you took, maybe you learned how to do polynomial division, or polynomial long division, and that would have helped you put f of t into a different form that would be equivalent but a lot easier to take the antiderivative of. Because it's kind of difficult to take the antiderivative of this rational function, but if I just do 30t plus 200 divided by t plus 2, I'll show you what we get. We ask ourselves, how many times can t go into 30t? And when we say that happens 30 times, because 30 times t is 30t. And also, I consider that 30 times 2 is 60. And I put parentheses around it, and I subtract. And 30t minus 30t is 0. 200 minus 60 is 140. T can't go into 140, so this is my remainder. And so I'm going to write my quotient as 30 plus 140 divided by t plus 2. So we do remainder over divisor. And this is my quotient. And so this is an equivalent way to write f of t. I could say that f of t is equal to 30 plus 140 times 1 over t plus 2. And this is exactly the same as that rational function f of t that we gave you. But anyways, let me write f of t as 30 plus 140 times 1 over t plus 2. And for my integrand down here, I want to find what is f of t minus g of t. So I'm going to subtract g of t. And g of t is going to be, well, I'll write minus 1/2 t and then minus 30, because I'm subtracting this whole g of t thing. 30 minus 30, that cancels out. And so for f of t minus g of t, I'm going to have 30 minus 30 cancels. And so I end up with f of t minus g of t. My whole integrand is going to be 40 times 1 over t plus 2 minus 1/2 t. And what if I want to find the antiderivative of this thing, the antiderivative of f of t minus g of t? Well, the antiderivative of 1 over something is natural log, and the antiderivative of t is t squared, and then I have to divide by a 2, so that'll be minus 1/4 t squared. And I need to plug in my upper bound and my lower bound into this antiderivative. So if I take let me call this function like capital H or something. That means that capital H of t is going to be 140 times natural log t plus 2, right? Minus 1/4 t squared. That's my antiderivative of my integrand. And so I just need to figure out what is this function at 15.8 and what is this function at 9. And you're going to need a calculator to evaluate that natural log. So 140 times the natural log of 17.8, remember because it's 15.8 plus 2, so 17.8, minus 1/4 times 15.8 squared. And the number I get is 340.7. And then plugging in 9, I get 140 times the natural log of 9 plus 2, so natural log of 11, minus 1/4 of 9 squared, so 1/4 of 81. And the number I'm getting now is 315.5. If I subtract the two, 340.7 minus 315.5, I get the answer 25.2. And so there's going to be 25.2 million barrels of gasoline that are exported between 2009 and September of 2015. That's the area represented here. This area is 25.2. That's how you would do it sort of the proper way. One thing I saw a few of you do, and but I really, really like, I appreciate this a lot, is that students would see this and maybe not know how to do it, or maybe be struggling with a lot of the math, because that was a long problem. I didn't expect anybody to get this because it was really difficult. But I saw some students do a Riemann sum approximation. Like maybe they realized that what they needed to do was evaluate the rate of gasoline production at each year. And since it was an annual rate, they just had to calculate what was the value of that function and then like add them all together. And so if you calculated f of 9, and then f of 10, and then f of 11, and then f of 12, and then f of 13, and f of 14, and f of 15, and added them all together, that would be a really close approximation to how much total gasoline was produced between 2009 and 2016. And then if you did the same thing for the demand function, if you evaluated g of 9 and g of 10 and g of 11 and g of 12 and g of 14 and g of 15, that would also be a really close approximation of how much gasoline was consumed between 2009 and 2016. And then if you took that first approximation minus your second approximation, it would be a really close approximation of our final answer. You would have actually gotten really close to 25. And so sometimes there's a nice like scrappy approach to things, right? Where if you can't figure out the proper way to do it, maybe you can be clever and put in a little bit of extra elbow grease and find the answer anyways. And likewise, for this first question, for the question, at what time does gasoline demand exceed production rate? I also saw students do the same thing. They plugged in f of 9 and f of 10 and f of 11 and f of 12 and f of 13 and f of 14 and f of 15, 16, 17, and so on. And then they did the same thing for g, and they looked for the moment when does my g function finally become greater than my f function? And you would have found that t equals 16 is the first time when g is greater than f. And you would have gotten credit for realizing that sometime between 2015 and 2016 is where the trade-off occurs. And so again, that's not the easiest way to do it. It's not the most exact way to do it, but it is a nice scrappy approach. If you forget what you were like supposed to do, that would still work. So I did give partial credit and props to any students that figured an approximative method, because that's just as valuable. Okay, that's the solutions to the exam. Like Cyrus noticed, today we are going to do calculus in more than 2 dimensions. We're going to talk about functions in 3 dimensions, which just means we're going to have 2 independent variables and 1 dependent variable. And so like this says, when a function depends on more than one input variable, we call it a multivariable function. And so this equation right here is just saying z is a function of x and y. So I call my x and y variables my independent variables because I actually have to plug values for x and y in as inputs to the function. And z would be my dependent variable because the value of d depends on x and y. So this function, if I write z equals 2 minus x squared minus y squared, this is a function with one dependent variable z and two independent variables x and y. You have to tell me what the values of x and y are before I can calculate my value z. So if we say that x is 2 and y is 3, then I just plug in 2 for x and 3 for y, and I find that z is -11. That's how it works when you evaluate a multivariable function. And you've actually done this before. Like maybe in geometry, you were given like an equilateral triangle, but instead of just a triangle, maybe it's a triangular prism, like this. And you're asked, what is the volume? Well, the volume of a prism is just the area of the base times like the height or the depth of the prism. So we'll call it the height. This would be the area of the base. And the area of a triangle is just the base of the triangle times the height of a triangle. And if we have an equilateral triangle, then that means all of the edges, all the angles, of the triangle are 60 degrees. And that means this, if I split the triangle in half of that angle would be 30 degrees, and that means this is a 30, 60, 90 right triangle for half of the triangle. And if my side length is, my side length is 1, then half of that side length is 1/2, and in a 30, 60, 90 triangle, that means I'm pretty sure I'm gonna have to think about this for a moment. Does anybody have the 30, 60, 90 memorized? I know it's going to be square root 3/2 for one of these. And I can't remember what the side length is. Is it like 1? Let me just see if that works out as like the Pythagorean theorem, right? So Pythagorean theorem is a squared plus b squared equals c squared. So if I have half squared plus 1 squared, that would be 1/4 plus 1, which would be 5/4. And if I take the square root of 5/4, that is not going to work because that would be √5/2. So this can't work. That's not a triangle. Maybe the hypotenuse is 1 and this is √3/2. √3 would be yeah, that would make more sense anyways, because √3/2 I'm pretty sure is less than 1. Let me do that in the calculator really quick. If I do √3 divided by 2, well, √3 is less than square root of 4, and square root of 4 is 2. 2/2 would be 1, so √3/2 has to be less than 1. Yeah. Okay, so that makes more sense, because your hypotenuse should be the longest side of your triangle. So let me try this again. One side of my right triangle is 1/2, another side is √3/2, and the hypotenuse is going to be 1 if I'm correct here. So root 3 over 2 squared, that would be, well, root 3 squared is 3, and 2 squared is 4, so that would be 3 over 4. 1/2 squared is 1/4. Half times half is 4th. And 4th plus 3/4 is 1. Okay. I'm feeling pretty confident about that. If you ever forget your triangles, your special triangles, your 30, 60, 90 triangles, or your 45, 45, 90 triangles, I remember that one of them has a square root 3 in the side lengths, and then another one has a square root 2 in the side lengths. And sometimes you just have to mess around with it in order to figure it out. You have to sort of reason with yourself. Like, I'm pretty sure since I already used the square root 3 that the 45, 90 triangle would have a hypotenuse of 1, and these side lengths should be square root 2 over 2. But if I'm not sure, let me try out the Pythagorean Theorem and see if it works. So I should have a squared plus b squared is equal to my hypotenuse squared. So 1 squared is just 1. Square root 2 squared should just be 2, and then 2 squared should be 4. And that goes for both of these side lengths. So I should get 2 over 4 plus 2 over 4 equals 1, and that checks out. So I think I've got my special right triangle sorted out. I just, sometimes if it's been a few years since you took a class, forget it. You have to sort of reason with yourself until you get it again. So anyways, the area of a equilateral triangle then should be the base, and the whole distance across the base I'm saying is side length 1. And then times the height, which in our case is root 3 over 2 for the height, and then times half, because the area of a triangle is 1/2 base times height. And then the height of my prism here is supposedly 6, and so this would be (3 divided by 2 times root 3, so it'd be like 3 times root 3 over 2 as my volume. But what I really want to illustrate with this example is that whenever you find this volume, you're basically solving or evaluating a multivariable function. Because my volume is a function of a few things. It's a volume of the side length of the triangle and the height of the prism, right? And so specifically, this function would be, your side length times 1/2 times root 3 over 2, and you would want to square it. So this part of my formula would be the area of the base, the area of the equilateral triangle, and then I would want to multiply by the height of my prism. So this volume of a prism, that is a multivariable function. Your independent variables would be the side length and the height of the prism. Your dependent variable would be the volume of the whole thing. So you have to tell me what the side lengths are and the height, and I'll tell you what the volume is. Anyways, you've seen multivariable functions before, just maybe in a different context. So in example 2, it says a person's body mass index is given by this formula, where W is your weight in pounds and H is your height in inches. And so the first question says, calculate the BMI of someone who weighs 200 pounds and is 5'10" tall. Well, notice that this BMI is a dependent variable, and it's a function of both the weight and the height of the individual. So weight and height are independent variables. You've got to specify those in order to figure out BMI. So if we were going to do this, it would be 703 times 200 divided by, what is 5 feet 10 inches in inches? Yeah, it would be 70 inches, so it would be 70 squared. So 703 times 200 divided by 70 squared gives me a BMI of 28.7. Anyways, this is the idea. You've got to specify your independent variables, and then you can calculate your dependent variable. So at the bottom of the page it says, when we had single variable functions, we could represent the function with a curve that lives in the xy plane. So like if I give you the function y equals x squared, this is what we call a single variable function because we only have one independent variable. You tell me the value of x and I'll tell you the value of y. So x is independent and y is dependent. And then I could plot it with a little curve that exists in my xy plane. But if we have a function of two variables, like this function is a function of two independent variables, then we're going to need a three-dimensional space, and we're going to have an x-axis, a y-axis, and a z-axis, where the z-axis sort of points up. And then we can be able to represent our function as a surface that exists in the space instead of just a little curve in the plane. And so this is my function z equals 2 minus x squared minus y squared, and it's kind of going to look like a parabola if you slice it in any way. And in fact, this shape is called a paraboloid. That's the name of this three-dimensional surface. It's paraboloid. And there's a whole bunch of free graphing calculators on the internet that you can find. They don't all work that well, but I've showed you the output of several of these graphing applications, and each of them has pros and cons, right? And so we call the xy plane the plane that exists horizontally, and then your z-axis is always the one that points up vertically. And so I can label these as x, y, z, x, y, z. Here we have x, y, and z. And then in this last one in the bottom right, we just have x and y. Okay. So I think this first curve top left is the prettiest looking one. If you choose some value of x, right, you have to tell me what my values of x and y independent variables are. You choose some value of x, like right here, whatever value of x that is, and you choose some value of y, like maybe this one. You just have to find the intersection of your x and y values in the xy plane, and that tells you where you should travel up from to find your surface. And then if I go straight from my point along my surface horizontally directly over to the z-axis, then that tells me my output of my function. So the output of my function is going to be the height of my surface above the point xy that exists in my xy plane. So, if you told me that x is 2 and y is 3, this would be 2 minus 4 minus 9, then z is negative 11. So if this point corresponds to x equals 2 and this point corresponds to y equals 3, then, well, apparently it doesn't because this is a positive value. It's above the plane. If your z-axis is above the xy plane, that's positive values of z. And if your z value is below the xy plane, that would be negative values of z. So maybe I need to find smaller values of x and y to talk about. Like if x is half and y is half, then 2 minus 1/4 minus 1/4 would be 1.5. My z value would be 1.5. And so maybe this point is half in the x direction, and this point is half along the y-axis. So this point right here is when x value is half, y value is half, and then the output value of my function should then be 1.5 up along the z-axis. The height of my surface above the xy plane should be 1.5 at that point. Okay, so let's talk about some of the pros and cons of the rest of these visualizing techniques. So I like this for a specific reason. And if you look only at the blue lines, like I've done over here, these blue lines are moving just in the x direction. So for any blue line, we would say that my y value is fixed, right? So maybe this blue line might correspond to y equals half, right? So if I say y has to be a fixed constant value, the only thing that's changing is going to be the x value and the z value. So you can see for a fixed y value, what you would get out of your function for z if you change the x values. And then in green here, these green curves move just in the y direction. And so we're saying I'm choosing an x value for each curve, and then x has to be fixed. So if I give you a specific x value, which is maybe the x value, x equals like 1 or something, right? Well, then as you change the y value, your z value will still be changing, but you're specifically choosing slices of my surface that have a fixed x value. And whenever you combine these two, then you get this nice grid pattern. And so you can sort of still see the surface, but also see how your multivariable function is changing just in one variable. So the last things on the bottom of the page, these are both called contour lines. And the neat thing about contour lines is contour lines have a fixed value of z. So at every point along this circle, maybe the value of z is 1.5. And at each point along this circle, the value of z is 1. And maybe at this point, at this circle, the value of z is 0. But everywhere along the contour line, your multivariable function has the same output value. And if I were to take my camera and situate the center of my camera lens directly above the z-axis and look down at my surface, and I'm looking at the contour lines, this would sort of be the bird's eye view of my contour lines. So again, if I'm way up high along my z-axis and I'm looking straight down the z-axis, so my entire z-axis would be like right here at the origin pointing up out of the plane towards me. This is going to show me the relationship between x and y that gives me fixed values of z. So if I want a value of z, and let's see, if y is 0 and x is 1, what would my value of z be? If y is 0 and x is 1, that would be 2 minus 1. So this red circle in the middle, this is the contour line that corresponds to z equals 1. So if you want the output exactly 1, you have a whole range of values you can choose for x and y. Any point along this red circle represents a combination of x and y values that give you z equals 1 when you plug them into your function. So anyways, contour lines are important for that very reason. If we're looking at the function z equals x minus y, then as I go along the x direction, my surface is increasing in value, right? Because if x becomes bigger, then z should also become a larger value. But if I go in the y direction, if y is increasing, that should actually decrease my value of z. So if I go out along the y-axis, then the value of my surface, or the value of my z, should be decreasing, right? And so this is what we see happening in this plane. If you go farther on to the positive x-axis, your surface is higher. If you go farther along the positive y-axis, your surface is lower. So you get this slanted plane. And if I were going to make contour lines, these are fixed values of z represented on the xy plane. So if you want the specific value, for example, z equal to 0, all you have to do is make x and y have the same value. So like when x is 1 and y is 1, you would have z equals 1 minus 1, which gives you 0. Right, so contour lines always give you fixed values of z. This is a nice function, and I want to illustrate this one to you a little bit better. So on the left is the surface, and on the right is the contour lines for that surface. And let me try to pull up, I don't remember the name of my 3D calculator I was using here. I think I found it. The internet in my office is really fast, but the internet in this classroom is like very slow. This calculator that says David Math Logic is really, I think it makes really pretty graphs, but it's really buggy. It like crashes all the time, so it may or may not actually load. GeoGebra is a really powerful tool that has a lot of neat features, but it's really, really difficult to use GeoGebra. So these all have pros and cons. I'm just really sad that this isn't going to load for me. I've been really frustrated with the 3D graphing calculators that are available on the internet. So I've been trying to write my own program to do it, but it's not ready yet this year. I'm going to use GeoGebra, and I want z equals x squared minus y squared. And so, there we go, that's not bad. So, again, GeoGebra is a 3D calculator, so along the red axis, that red axis is going to be my x-axis. And as x is increasing, x squared should be increasing, so my z value, or the height of the surface, is increasing as I move out along my red axis. In fact, if I just look at the side view, so I'm only looking at the effect of my x-axis here, we're essentially saying that y is 0, that would simplify my function to z equals x squared. And x squared is a parabola, and you can sort of see that parabola shape on the side. What if instead I forget about my x, let's just set x equal to 0, and only consider what happens in the z equals negative y squared. Well, negative y squared is a downward facing parabola, and you can see that downward facing parabola shape up here if I forget about my x-axis. But taking the whole thing as a total, it sort of looks like a Pringle, it sort of looks like a potato chip. Or alternatively, if you're a horse person, this sort of looks like a saddle. It looks a little bit like you could sit there and it goes up on the back and up on the front, and then it goes down along the sides of the horse. And For this reason, mathematicians call this point in the middle, which is a minimum in the x direction and a maximum in the y direction, we call this a saddle point. And so whenever you have a minimum in one direction that's also at the same point a maximum in another direction, we call that a saddle point. So that function is what I'm trying to show here. And the contour lines are a little bit interesting in this case. Imagine trying to draw a contour line that has a fixed value. Like maybe I want the contour line at z equals 0.2. It gave me a plane, but it's not. It's a really wimpy plane. Like I don't know why it stops there. I know. Like why did it stop? I don't know why it doesn't extend a little bit more. Okay, there it goes. Now it's touching the. Okay. Like I said, GeoGebra sometimes has neat features, but sometimes it's hard to use. So look at the intersection between the blue plane and the red curve. That intersection, that would form my contour line. That's specifically the contour line for whenever z is equal to 0.2. And, you know, here in my contour lines, let's say this is my x-axis and this is my y-axis, then maybe this line is the contour line for z equals 0.2, and also this would be the same thing. So my contour lines are actually hyperbolas whenever I have this weird saddle-shaped thing going on. Okay, this is also a paraboloid, but this is an upward-facing paraboloid. So I have z equals x squared plus y squared, and whether you looked at it from the side, either way, your slices of this would look like a parabola in either the x or the y direction. So again, my contour lines are nice and easy. My contour lines are circles here. And this last function is the big island of Hawaii, which is an excellent place to visit if you haven't already. Lots of stuff to do here. This is called Mauna Kea, and it's this nice mountain. It's got a big snow cap year-round. There's a lot of big observatories up there because there's not a lot of light pollution when you get that high up on an island in the middle of the Pacific. Nice place for observatories. This is Mauna Loa, and so this is a volcano over here. But what I want you to notice is that this on the right is called a topographical map. It shows you the topography of the island. And what's drawn on the topographical map are contour lines. So each one of these lines represents a curve of constant elevation. Everywhere you go along this line, it looks like is going to be 7,000 feet. So along the whole length of this line, you could walk exactly along that path and you would never go uphill or downhill. You would always stay exactly at 7,000 feet elevation. So that means if you go in the direction where you're rapidly crossing a bunch of contour lines, then you're going to be going rapidly. You're going to increase your elevation very rapidly. You're ascending as fast as you can. You're going in the direction of the steepest ascent. And likewise, if you go, you know, maybe you'd make this trip, like, yeah, your elevation is increasing, but it's increasing very slowly because you can see that these contour lines are actually spread apart fairly well. So anyways, I think a lot of people are familiar with topographical maps, and so sometimes that helps this concept of contour lines to click, because these contour lines are just a topographical map of a surface in 3 dimensions. Okay. So we'll see how much we can get done in the next 11 minutes here. Example 3 says, well, it has the same BMI formula, which we talked about how that's a multivariable function. And the question says, determine the equation for the contour lines corresponding to different BMIs. So let's think about the BMI 20. I'll just pop in 20 for my BMI, and 20 is equal to 703W divided by h squared. So I could write this as 20 h squared equals W, and in fact I could divide, 703W, and I could divide by 703 and write the formula W equals h squared times 20 over 703. So basically, you tell me your height, I'll plug that in for h squared, and then I can tell you exactly what weight you need to be to have a BMI of 20. And notice what happened to my BMI. My BMI of 20 just ended up over here. So if I wanted the BMI contour line for 24, I could write the formula W equals h squared times 24 over 703. If I wanted the contour line for 28, I could just say W equals h squared times 28 over 703. And if I wanted the contour line for 32, I could write W equals h squared times 32 over 703. I'm just curious to see what this would look like. So if I say that W is going to be my y, and h is going to be my x value, because Desmos only deals in y's and x's. My contour line for BMI of 20 would be 20 divided by, oops, divided by 703, and then I have a few others that I want to do. I want the contour line for 24 BMI, 28 BMI, and then 32 BMI. Now again, x represents my height, and you can't have negative height, so maybe it's better to look over here. And y is representing the weight that you would need for a specific BMI. So as height increases, your required weight for the specific BMI would increase. And the weight is lower for lower BMIs, so this is the curve for BMI equals 20, this is BMI equals 24, 28, and 32. And this sort of contour lines is telling me that over here, my surface of BMI values is increasing relatively slowly in this direction, but over here, it's increasing relatively quickly because the contour lines get close together. And so let's look. It looks like it froze on me. Oh, maybe not. Okay. I don't want that one. I don't want that plane. So my function was that BMI is equal to, I already forgot it, 703W over h squared. So I'm going to write 703x divided by y squared. No, I was letting x represent my height, so I need to make that 703y divided by x squared. Not that it really matters if we're just looking at the pretty graph, but okay, I'm zoomed in too far. I need to zoom out to give the surface a little bit of character to it. Nice. Okay. So red is my positive x-axis, green is my positive y-axis, and blue is going to be my z-axis. So you can see the height of my surface is increasing whenever my body weight is increasing, and then it's decreasing whenever my height is increasing. And just like the contour line showed, if I get close to the origin, it increases really rapidly, and if you're farther away from the origin, it increases more slowly. But we could have, like I said, we could have gotten that just by looking at these contour lines. Okay, number 4. says determine a formula for the total cost of materials of an aquarium where the base is made of metal that costs $35 per square foot and the sides are made of a sturdy glass that costs $15 per square foot. And I guess there's no top to this aquarium. It's just like this. And so I'm going to have, I don't know, some length and some width and some height. And for the sides, I'm going to have two sides that are the width times the height in area, and I'm going to have two sides that are the length times the height in area. And then I'm going to have one base that's the width times the length in area. But now I need to multiply those side areas times 15. And I need to multiply the base times 35 because that's the dollars per square foot. And so this is going to be my total cost as a function of length, width, and height. And so I would say that my cost is a function of length, width, and height of the aquarium. In the sense that length, width, and height are independent variables. You have to choose what you want your dimensions of your aquarium to be and then tell me. And then I'll use my function to tell you the dependent variable, which is going to be the total cost of materials. So if I have x squared plus y squared equals 1, that turns out to be the formula for the unit circle centered at the origin with radius 1. And so if you plug in y equals 0, then x squared equals 1, then x has to equal 1. And the same thing if you plug in x equals 0, then y squared equals 1, so y has to equal 1. So it makes sense that your function has to or the curve represented by this equation has to be going through these points. But what makes it exactly a circle is that x squared plus y squared equals blank. That looks like the Pythagorean Theorem if I just make 1 into 1 squared. So of course 1 is 1 squared, and you know the Pythagorean Theorem is just a squared plus b squared equals c squared. If I fix the hypotenuse of my triangle to be equal to 1, then I'm saying the other two sides have to be fixed or have to be locked into this relationship where if I make a right triangle with those sides, then the hypotenuse is 1. So x is in this horizontal direction, and y is in this vertical direction. So since one's horizontal, one's vertical, that means there's a right angle in between these. And then the hypotenuse, if I make sure x squared plus y squared is 1, the hypotenuse is 1. And even as I change my x variable, if y is locked into this relationship, then it should always be 1 away from the origin, and the shape, who is always 1 away from the origin, is a circle, right? So that's how it works. We're going to see really quick on GeoGebra that if I add z now, x squared plus y squared plus z squared, this is going to give me a sphere with radius 1. So hopefully it loads one day. Okay. X squared plus y squared plus z squared is equal to 1. And the reasoning is still pretty much the same. You need to use the Pythagorean Theorem to really prove that this is true. But we don't really have a whole lot of time left in class, and so I think I'll skip that full explanation for why that happens to be the equation for a sphere. The last thing I'll say before I let you guys go is whenever it says the trace along the x-axis, you're going to set y equal to 0. Because the x-axis is just the point in the xy plane where y is equal to 0. and then we want to plot z as a function of just x, right? Because if I set y is equal to 0, then z would be 1 over square root x squared, so it would look like 1 over x for that trace. If I want the trace along the y-axis, then I would set x equal to 0, and then plot z equals a function of only y. And if I set x equal to 0, then it would be 1 over square root of y squared, so it would look like 1 over y. And so that's what the trace is. It's saying eliminate one of your variables by just setting it equal to 0, and then plot the resulting function of z as a function of either x or y. And then again, we already talked about contour lines. And we also talked about what it means for contour lines to be directions of ascending the fastest or descending the fastest, or staying the same altitude as you walk around a mountain. Would be walking a path exactly on top of a contour line. So you could take a look at these pictures up here to answer those questions, right? If you were looking at these contour lines, you know that the height of your surface is changing pretty rapidly over here where they're all bunched together. And you know, if you walk exactly along the contour line, you're keeping a specific value of z. And if you go in this direction, maybe that's the direction of slowest descent. All right. So you're free to go. If you have any questions, you can stick around and ask me. But
I do have a question.
What's up?
You think maybe you could post the exam corrections on Canvas? Kind of do that.
No, you guys need to work those out on yourself.
No, but those are, you want us to do the correction, right? Like the other tests. Okay.
Yeah, just like the other midterm exams, you can do corrections on this one.
I do have a question on, number 7 on the exam. So I noticed when you took the derivative of the natural log of 3t, we dropped the 3. Why is that?
Okay, that is because of derivative chain rule.
Oh.
So you were right that whenever you see the derivative of natural log 3t, you think, well, the derivative of natural log would be 1 over whatever's inside that natural logarithm. But then the chain rule says I have to take the derivative of my outside function and then multiply times the derivative of my inside function. My inside function here would be 3 times t, so the derivative would be 3, and then those 3's are going to cancel.
Oh.
Yeah.
I see.
So that's tricky.
Yeah, because I kept
It's kind of a weird.
And I think that's probably what we got cut. Yeah, I think that was my question.
Chris had asked me to pick up his test form so he could do correctly. Would you mind giving that to me?
Yeah.
Or I will take it.
You can actually do these three.
Oh yeah, the notes too.
All right, y'all have a good weekend.